Derivatives of trigonometric functions. So this is now section 3.5. The derivative of the sine function is the cosine function. So it says here that if we take the derivative of sine x, it turns out that it's equal to cosine of x. Now how do we show that? Well, let's look at the definition of what's a derivative. Remember that the derivative of f of x is equal to f prime of x, or sometimes we refer to it as the derivative of f of x with respect to x, and we say it's the limit of f of x plus h minus f of x, and the whole thing will be divided by h. And here is where, in order to show that this is true, that the derivative of sine x with respect to x is cosine x, we're going to need these three bullets. The first one is the sum identity for sine of a plus b, and if you go back to your trigonometry, that's equal to sine a times cosine b plus cosine a times sine b. And then we've used this theorem before, that the limit of sine of an argument divided by that same argument, so in this case it's h, so the sine of h over h as h goes to 0 is equal to 1. And another one is that the limit of cosine of h minus 1 whole thing divided by h as h approaches 0 is equal to 0. So where do these things come out? Once we apply the definition of the derivative into our sine function. So the derivative of the sine of x with respect to x is equal to the limit of, what do we put in this place? We now write the sine of x plus h minus the original function, the sine of x. The whole thing will be divided by h, and we let h approach 0. So according to the sum identity, that's how we will expand the first term here. So this is now equal to, well, I'm going to write it here so I'll have enough room. So it's equal to the limit of, let's expand sine of x plus h using the sum identity for sine of a plus b. So it's going to be sine of x times cosine of h. Okay, and then it follows the sine, so we put a plus here. And it's now cosine of x times sine of h. So what is this so far? So far this is just this term, minus sine of x. And then the whole thing is divided by h. Where do these come in? We really want to see that we get this expression as well as this expression, which means we're going to shift around a few terms and just rearrange them. So I'm going to need this together with this, and then this is by itself. So let's go ahead and rewrite that. So it's equal to the limit of, okay, I'm going to rearrange, so sine of x cosine of h minus, I'm going to put this together, minus the sine of x, and then separate them into two fractions over h. And then of course we got this one too, so plus cosine of x, and then we have, what do we have? Sine of h whole thing divided by h. Alright? And do you see where this now comes in? When we take the limit as h approaches 0, then what do we have? It's now equal to the limit of, pull out the sine x here. So let's go ahead and pull out the sine of x. And then what's left is cosine of h minus 1 divided by h, okay? Then plus, we've got cosine of x, and you multiply that by, I'm going to separate it that way, it'll be obvious, sine of h over h. Okay, we are going to let each of these approach 0. So when h goes to 0, this whole thing goes to 0. This whole ratio from here is equal to 1. So what is the surviving term? It'll just be cosine of x. So the limit as h approaches 0 is just cosine of x. And there, we have shown that the derivative of sine of x is equal to cosine of x. And now it turns out that if we take the derivative of cosine this time, we get negative sine of x. How do we do that? Just like the previous slide, but instead of using cosine, we now apply cosine and into x plus h. So that's what the identity that we'll use. And this is one exercise that you can work on and then see if you can try to prove that the derivative of the cosine of x is equal to minus sine of x. Now, what does this show? It just shows the relationship between the original function cosine x and its derivative function. And remember, when we were trying to do that, we see how it pairs up with the derivative function by looking at the lines of the tangent lines to the curve. So if we start off here, we can see that the lines tangent to the curve have negative slopes here. And then it becomes 0, and that corresponds to an x-intercept on the derivative function. And then from minus pi up to 0, these are all positive slopes. So when we have an increasing part of the function, you get positive side of the derivative function because this means that the slopes are all positive. And then we hit again a horizontal tangent, so that's why it occurs at x equal to 0, so that gives us a graph, the derivative function passing through the origin. And then of course these are all negative slopes. And what does that tell us? From 0 to pi, your derivative function should be negative right there. And then we hit another horizontal tangent, so that's another 0, until we go further, and those are positive slopes right here, which makes the graph positive as well for the derivative function. And see, this is actually the sine function, because what does the sine function look like? It's this one. So the red is its negative. So this is y equal to sine x, and this is y equal to minus sine x. Now, finding the derivative of tangent of x. We will not use the definition. Instead, we will apply the derivatives already of the sine and the cosine function, and apply that to tangent. Because what is tangent of x? Do you remember what tangent of x is? Okay, it's what? Sine over cosine. So we are now going to take the derivative of sine over cosine using the quotient rule. So now to take the derivative of tangent of x with respect to x, I'm going to use the notation prime. So, I want you to get used to different kinds of notation. So let's write tangent as sine of x over cosine of x. And we take its derivative. And then, what is the quotient rule? Square of the low we go. So cosine square x at the bottom. And then first take the derivative of the top. So what's the derivative of sine x? It's cosine of x. Multiplied by the bottom, so you get another cosine of x here. Minus, what's the rest of the term on the top? It's the top sine x multiplied by the derivative of the denominator. So what is the derivative of cosine of x? Minus sine x. And so let's go ahead and simplify. This now becomes cosine squared x, and then negative times negative is positive sine squared x. Whole thing is divided by cosine squared x. Okay, going back again to your trigonometry, what is cosine squared x plus sine squared x equal to? Remember, that's your unit circle, so this should be equal to 1. So the numerator is just, this whole thing is just equal to 1. So we now have 1 over cosine squared x. And what is cosine squared x? Remember, what's the reciprocal of cosine x? It's secant. So this is now equal to secant squared x. So we have shown you that the derivative of tangent x is equal to secant squared x. And then, you know, try out doing the secant, try deriving the cotangent and the cosecant. That's a good exercise. But these are the derivatives that we need to remember alongside what? The derivative of sine x and cosine x. Okay, here we've got number 1. It says find the derivative dy by dx of these two problems. Let's go ahead and work on number 1. We need to find dy by dx, which means it's just y prime. So I'm going to ahead and use y prime. And what is the derivative of minus 10x? It's just minus 10. And then, what is the derivative of cosine of x? Well, we know it's minus sine x, so it's plus 3 times minus sine x because it's just a multiple of cosine of x. And so rewriting this or simplifying, we have minus 10 minus 3 times the sine of x. There's your dy by dx. Let's work on number 2. Okay, but number 2, we need to rewrite y first with looking at the first term as 3 times x to the negative 1 so that we can use the power rule. And then plus 5 sine of x. So what is y prime? Y prime is negative 3 x to the, what do we do here? Take off 1, so minus 2. And then plus 5 times the derivative of sine is cosine of x. So there we have it. That's the same as negative 3 over x squared plus 5 cosine of x. Okay, number 3. Now we have two expressions here. You have x squared and the cosine of x. So what we have is a product of two functions. One function is x squared, another function is cosine of x. So what we'll do, we'll treat this as a product, apply product rule, and use as well as a derivative of trig functions. So let's do that. So now y prime is, first take the derivative of x squared, and that's 2x multiplied by cosine of x. Okay, and then take x squared multiplied by the derivative of cosine. So you put minus sine of x. So we have, thus far, it's 2x times cosine x minus x squared sine of x. All right, moving along. Let's look at number 4. We have to use product rule again here, and as well as the sum rule by taking the derivative of a constant. But let's rewrite this again so we can apply the power rule. How do we rewrite the square root of, rewrite the square root of x using the power rule? Okay, we'll rewrite y equal to x to a half multiplied by secant of x plus 3. So what is y prime? Y prime would be, okay, take the derivative of the first term, so that's 1/2 x to the 1/2 minus 1, that's negative 1/2, multiplied by secant x, and then plus x to the 1/2 multiplied by the derivative. Now what is the derivative secant of x? It's equal to secant x times tangent of x. And then what's the derivative of 3? 0. The derivative of constant is 0. And okay, so now we've got secant of x divided by 2 times the square root of x. Where did that come from? You bring down that. Plus square root of x secant x times tangent of x. There we have it. We've used the product rule as well as the sum rule. That's why it's 0 there. Now, number 13. I have a question for you. Since you have these two ratios, do we apply the quotient rule, or should we just go ahead and rewrite these using their trig identities? Because these are reciprocals. So that means we go y now. We can rewrite as what is 1 over cosine. So that's the same as 4 times secant of x. And then what is the reciprocal of tangent? It's cotangent of x. Are we ready to take the derivative? Yes, indeed. So we take y prime equal to 4 times, what's the derivative of secant? It's secant of x, tangent x. And then what's the derivative of cotangent of x? It's negative cosecant squared x. And there you have it. If we had used the quotient rule for these two, oh, that's a lot of work, and we don't need to do that. All we need to do is rewrite them first as their reciprocals, and then apply the derivatives of trig functions. And we're done. There's y prime.